Okay, now we understood how start was written as AD comma 01. Okay, now the second part of the instruction is its operand, that is 201. So we tried to rewrite it into some other form as C comma 201. So C denotes it's a constant and comma its value, that is 201. Okay, so C denotes the constant, comma followed by the value of the constant, that is 201. Now moving to the next instruction. The next instruction is mover. Again, referring to the OP tab, we will get to know that this is of type imperative statement and its mnemonic info is 04. So we replaced this move R by is comma 04. It is obvious the LC is going to be 201 because initially LC was 0. Okay, and once we get the start instruction with the operand as 201, we updated LC as 201. Now this move R instruction is of imperative statement type. So for all the imperative statements we perform a location counter processing. So the location counter will be the current LC 201, and once we are done with the statement move R, we will increment LC by 1 because the length of each imperative statement we are considering as 1. So next LC is going to be set to 202. Now move R is uh, retranslated into some other form as is comma 04. A register we are writing it as 1 because in a hypothetical language we are having 4 registers: A register, B register, C register and D register. So each register is being identified by its unique number, that is A register by 1, B register by 2, C register by 3 and D register by 4. So for our example over here, in the case we had A register, so we will be replacing A register by 1. Okay, now similarly if it could have been B register, we could have written 2 over here. Okay, now next operand is equal to 5. So if you remember, this is a literal. Okay, so literals are written using equal to followed by in single quote its value and again a single quote. Okay, so over here we have literal 5. So once we know we have a literal in the operand field, so what we will do is we will try to write write this literal in some other form, and this some other form is going to be its position in the literal table. So once we get the literal in the operand, we will be making the entry of this literal in the literal table like this is our literal table. Okay, so in the literal table we made the first entry as literal 5, and right now we do not know its address because we have not yet allocated memory to this literal 5. So leaving its address right now blank, we will just write it in some intermediate code form as L comma 1, denoting it's the first literal in the literal table. So its ordinal position in the literal table is 1, hence L comma 01. Now moving to the next instruction, that is move M. So move M will be is comma 05. A register we will be writing as 1 and X in the operand 2 field. So X is a symbol. So this is a symbol, right? So once symbol is encountered, we will be making the entry of this symbol in the symbol table if not already done. Okay, so this X is the first occurrence of this symbol X, so we will be making its entry at the first position in the symbol table. And right now the address is going to be blank because this is just the usage of X in the operand field, but X is not yet declared what exactly this X is. Okay, so its address will be blank. Now the LC is going to be 202 because this is imperative statement, and this X will be written as S comma 01, that is this is the first symbol in the symbol table. Okay, now similarly next instruction is having something in the label field. So if you remember, this label field will always carry a symbol. Okay, so treating L1 as the symbol, we will check our symbol table whether we have made entry of L1 or not, and if not made the entry, we will be making the entry of L1. So L1, okay, at the position 02. Now remember, unlike the operands, these labels are not required to be the part of the intermediate representation. Rather, whenever we encounter a symbol in the label field, that represents its definition of that symbol. So that particular location address will be the address of that particular symbol. So the current LC is 203 because after 202 we incremented LC by 1. So LC was 203. So as soon we make entry of L1 in the symbol table, at the same time we will be updating address of the L1 as 203. So hence you will find address of L1 as 203. Now next is move origin statement. Now origin, if you see in the OP tab, we will find this is assembler directive, hence no LC processing. Rather, origin will instruct assembler to set the LC as the result of this expression in the operand field. So this expression is L1 plus 3. So referring to the symbol table, we will get to know address of L1. So referring to the symbol table, we will get the address of L1 as 203. So 203 plus 3. So result of this expression is 206. So our LC will be changed to 206. So that is regarding this origin statement. So origin will be rewritten as AD comma 03. L1 will be written as S comma 02, that is it is a symbol and its ordinal position in the symbol table is 2 plus 3 as it is. Okay, now next instruction is LTORG. Let me remove, let us just remember LC is 206 and let me remove all the ink. So our LC is 206 right now, and we are at LTORG statement. So LTORG referring to the machine opcode table, we will get to know again it is an assembler directive. Now for assembler directive, no LC processing, and we will just capture LTORG and we will try to write it as AD comma 05. So referring to the machine opcode table, we will find this is the fifth assembler directive in that table. Okay, now what exactly this LTORG will do? So this LTORG will instruct assembler to allocate memories to the literals which are used prior to the statement and after the start. So it may be the case, otherwise there may be the case where we are encountering the LTORG second time. So over here the literals which are being used between these two LTORG are required to be allocated the memory, but in the first occurrence of LTORG it is obvious at the top we are going to have the start instruction. So between the start and LTORG, whatever literals are being used, so we will be allocating, or the assembler will be allocating memories to all those literals. Okay, so this case we are discussing over here because this is the first occurrence of the LTORG. So referring to the literal table, we will get to know only two literals memory entry is done in the literal table, x and 5 and, let me check it, 5 and 2. Okay, this 5 and 2. So this 5 and 2 will be allocated memory. So prior to this first LTORG statement, the addresses were not updated over here in the literal table. So LTORG will instruct to allocate memory and update addresses of these literals in the literal table. So current LC is 206. So first literal 5 is been given the location 206. That means at 206 literal 5 is stored, and considering length as one memory unit, next LC is going to be 207. So the second literal is 2, so its address is 207. And again at 207 literal 2 will be stored, and we will increment LC by 1. So current LC is going to be 208 by the end of this LTRG statement. Now in the intermediate form or intermediate code, what assembler does is assembler makes exactly the similar adjustment as that of a DS statement, DC statement. Okay, so DC statement is written as DL comma 01 followed by the operand value over here. Okay, so this 5 will be considered as a DC statement, DC 5, and this literal 2 will be considered as DC 2. Okay, now translating this into some intermediate form will give us DL comma 01, that is DC statement, and 5 as constant, that is C comma 5. DC comma DL comma 01, that is DC statement, and 2 as constant 2. Okay, now next statement is add, having next as its label. So this is going to be a symbol, so we will make entry of next in the symbol table, that is at location 3. And if you remember, whenever we encounter a symbol at a label field, it is its definition, so we need to make entry of it if not made already, and at the same time we need to update its address as current LC, which is 208. Okay, so at the same time we have updated its address in the symbol table as well. So far we have 3 entries in the symbol table, and only L1 and next have been given the address, but this 215 is not yet updated. Now next is subtract instruction, location counter 9, then branch on condition, LT. If you remember, we discussed the condition codes table, and LT is represented as 1. So you will find IS comma 07 representing to the BC instruction. LT is 1. Now over here this is a condition code, not a register. Okay, because this comes with the BC statement. Then back is comma 04, that is the fourth symbol in the symbol table. Now similarly, this is LTRG statement, again assembler directive AD comma 05, no LC processing. Then literal 1 and 2, that is between two LTRG statements, whatever literals we have used, so we have used 1 and 2. Okay, so we will be allocating memory to the literal 1 and 2. My current LC is 211, so 1 will be given the address location 211. So considering this as DC 1, so DC is DL comma 01, and this 1 is C comma 1. Next LC is 212, so again DC, considering it as DC statement 2, so this is going to be DL comma 01, C comma 2, representing the constant 2. Now next is pool table. Yes, so far we have 4 entries in the literal table, 5, 2, 1 and 2. Okay, and all these literals are being given the addresses. At the same time, if we look at the pool table, so the first pool of literal is starting from the first literal in the literal table. So if you see, the first pool is starting from the first literal in the literal table 5, and in the first pool if you see, we have two literals 5 and 2. Okay, so the second pool is starting from literal 1. So if you look at the position of 1 in the literal table, it's at number 3. So in the pool table, second pool of literal is starting from third literal in the literal table. Okay, now again the pool 2 of literals, if we see, we have two literals literal 1 and literal 2. So it is obvious the next pool of literals will be starting from literal number 5 in the literal table, that is this. Hence, third pool of literal will start from fifth literal in the literal table. Okay, so next instruction is back. Again, if we see, we have already made entry of back as back was used earlier. So we will just update address of back over here as it is encountered in the label field, and back. But over here, if you see, we have EQU statement. EQU is assembler directive, so no LC processing. So what address to be updated for back? Because I have already stated, whenever we encounter a symbol in the label field, it is its definition. It means we need to update its address as its current LC. But this is the exception where we have EQU statement. So EQU is assembler directive, so we are not going to have any location counter over here. So EQU statement will essentially it instructs the assembler to equate the value at the right hand side equal to the value at the left hand side. So back will be given the address of the result of the expression that we have in the operand field. Over here we have only L1. So if you look at the symbol table, we have address of L1 as 203. Okay, so back will be given the address of L1, that is 203. So in the symbol table we will update address of back as 203. So back address of back as 203. Now consider a case where instead of L1 we could have say L1 plus 2. So in that case we will be evaluating this expression, and the result of expression will be the address of back. So 203 plus 2, that is 205, could have been given the address of back. Okay, next is origin. Again it's assembler directive, so it asks assembler to set next LC as result of the expression next plus 5. So referring to the symbol table, we will get address of next as 208. 208 plus 5, that is 213. So next LC is going to be 213. So if you look at the next instruction, the LC given is 213. So similarly, all these instructions will be processed, and if required, addresses in the symbol table will be updated like over here. Okay, and once we are done with the end, we just need to look at the literal table. So in the literal table, this literal 4 was not given the memory, because after using literal 4, let me remove all the ink. After using the literal 4, no LTORG statement was encountered, right? So we do allocate memory to literals after LTORG statement, but this is the case where LTORG is not present. So literals are memory to literals are allocated either after LTORG statement or after end statement. Okay, so this literal 4 will be allocated memory after end statement. Okay, so by the time of this end statement, our LC was 215 plus length 1, that is the uh, operand of the DS, that is 1. So LC was 260. So after end, the literal 4 was given memory at 216, that is our current LC. Okay, so at the same time we updated its address as 216 in the literal table. Okay, so this is how the pass 1 of 2 pass assembler is done. So I guess it would be clear to you. In the next lecture I will try to explain another example of pass 1 of a 2 pass assembler. So this is just for your understanding how pool table was generated. So first, if you remember, first pool of literals were 5 and 2, second pool of literals were 1 and 2, and third pool of literals were 4. So how did we finalize that these two literals or these two literals belong to the same pool? So for that, what we should understand is our program starts from the start instruction, and after that whenever we get the LTRG statement, so all the literals used between the start and LTRG will fall under pool 1 of literals. Okay, let me rewrite it correctly. So all these literals will be considered as pool 1 of literals. Okay, now second case is, what if we have few more literals used after this LTRG statement? So for those literals, either we will get another LTRG statement to allocate memories to those literals, or we may not get LTRG, rather we will find end statement. So in this case, all these literals used after first occurrence of LTRG, that is between either two LTRG or between LTRG and end, this will be referred as pool 2 of literals. Okay, so in our example we had this LTRG, so I will just remove this end, and after this second LTRG again few literals were used, and finally we had end statement. So after second LTRG and end, all those literals that are being used will be referred as pool 3 of literals. Okay, so in our example, total we have 3 literal pools, that is all those literals between start and first LTRG, that is pool 1 of literals. Okay, then all those are pool 1 of literals. Then after this LTRG and second LTRG, all those literals which are used will correspond to pool 2 of literals, and second LTRG and end in between all those literals which we used will belong to pool 3 of literals. Okay, so that is what I tried to understand over explain over here. So we understood that total 3 pools of literals should be there, so the size of the pool table is going to be 1, 2 and 3. Okay, so first pool of literal is starting from which literal in the literal pool, literal table. So the first literal, that is 5, by which the pool 1 is starting, hence the entry is number 1 in the literal table. Then first pool had 2 literals, then second pool is starting from the third ordinal position in the literal table, hence number 3. Again it had 2 literals, then third literal pool is starting from number 5, that is number 5. So I hope this example would be clear to everyone. Still in the next video we will try to learn another example, and we will try to perform pass 1 of 2 pass assembler. Thank you.